Welcome to Lecture 3.3, the method of undetermined coefficients. Recall that this was the homogeneous plus particular solution method for first-order ODEs, where we first solved the homogeneous equation and then we guessed a particular solution of a certain form with some unknown coefficients, plug that back in and determine those coefficients. So we'll do the same thing here for second-order ODEs. And unlike first-order ODEs, this is really the only way that we have to solve second-order equations, unless we want to go the route of turning them into systems of equations, like we mentioned last time. Okay, so let's recall our two big ideas for first-order linear ODEs. The first one was that if we have a homogeneous ODE, that's something like this, where the right-hand side is 0, and we have two solutions y1 and y2, then any linear combination of those is a solution. Even though there's only a one-parameter family of solutions for first-order equations, we still have this principle, sometimes called the principle of superposition. The second big idea was for inhomogeneous ODEs, when the right-hand side is non-zero. Then, if we find any particular solution, any solution we can come up with to this equation, and we add it to the solution to the related homogeneous equation, just the thing when we make the right-hand side 0, then the general solution is just the sum of those things. So we're going to see that both of these don't just hold for first-order ODEs, but they hold for second-order ODEs as well. So here's the first big idea for second-order linear ODEs, and notice that it's pretty much the same as the first big idea for first-order linear ODEs, just the only difference is that this equation is second-order instead of first-order. So this says that if you have two solutions, y1 and y2, then any linear combination of them, or superposition, is going to be a solution as well. So let's verify this the same way we verified it for first-order equations. Namely, let's take this proposed solution, call it y of t, and let's show that it is, in fact, a solution. I don't want to call this a proof. That makes it more complicated than it needs to be. So we're just going to plug this thing into this equation and show that it does, in fact, equal 0. So the second derivative is just c1 y1 plus c2 y2 double prime plus p of t times the first derivative is c1 y1 plus c2 y2 prime plus q of t times, oh, I forgot my derivative right there, q of t times c1 y1 plus c2 y2. So we have to show that this is 0. So how do we do that? Well, we can break this apart, and so the derivative of the sum is the sum of the derivatives, and then we will group the y1s together and the y2s together. So let's do this as c1 y1 double prime plus p of t times c1 y1 prime plus q of t c1 y1. So there are the y1s. Let's put the y2s next. So c2 y2 double prime plus p of t c2 y2 plus q y2 prime plus q of t c2 y2. Okay, let's factor out these constants. So this is, I should say this is equal. So this is c1 times y1 double prime plus p of t y1 prime plus q of t y1, and then c2 times the same thing over here, y2 double prime plus p of t y2 prime plus q of t y2. And notice that naturally this equals 0. Why? Because y1 solves this, and that's exactly what it means to solve, is that this thing is equal to 0 for y1, and similarly, this is equal to 0 as well. So therefore, both of these things are equal, the sum of this is equal to 0, and that's exactly what we wanted to show. Okay, so here's big idea number 2. Says that the general solution to a second order linear inhomogeneous ODE is just the homogeneous solution plus any particular solution. So this part is the same thing as we had for first order equations. The only difference is that the homogeneous equation now is a 2-parameter family of solutions. So this is now YH of t, whereas for first order equations we just had a 1-parameter family of solutions. And I should say that this is true for inhomogeneous equations, but it's also trivially true for homogeneous equations, because when you have a homogeneous equation, 0 is a solution. Note why that's true. If this is 0, then plugging in 0 for y satisfies this. So in that case, well, this is true where a particular solution is just 0. But we only really need it for inhomogeneous equations. Okay, so let's also verify why this is true, and it's going to be very similar to what we did for first order equations. And here I'm actually not going to show you that the homogeneous equation is a 2-parameter family. That's a deeper theory that the proof of which is beyond the scope of this course. I'm just going to show you that, say, if you assume that this is YH, then this is the general solution. Okay, so as before, let's take the general solution. So let's say, okay, so why is this true? Let's consider y of t, the general solution, minus yp of t. And let's say this, so this is the general solution. So because the general solution, is going to have a 2-parameter. It's going to be something like this. It's going to have several constants of integration in it. It's a whole family of solutions. So it's an expression in terms of maybe C1 and C2. Whatever it is, we know that it will satisfy y double prime plus p times y prime, that's p of t, plus q of t times y equals f. I mean, that's what it means to solve this equation. And the particular solution satisfies that as well. So we have yp double prime plus different p here, say subscript, plus the particular solution prime plus q times yp equals f as well. So if we subtract these two equations, just like we did for first order equations, now we have y minus yp double prime plus p times y minus yp prime plus q times y minus, I should say that this is not q of y minus yp, this is q of t times y minus yp. And similarly, this is p of t times y of t minus yp of t. So this, where were we? This equals f minus f, which is 0. So in other words, this solves, so what that tells us is that y minus yp solves the related homogeneous equation. Come on. So in other words, let's let's go up here. So i.e. y minus yp equals yh, which is c1 y1. Here's what we're assuming: c1 y1 plus c2 y2. So that's the same thing as saying y equals c1 y1 plus c2 y2 plus yp. And that's what we had to show. And again, it's not a proof. We're not actually showing that every single solution is like this, although it's actually not much harder to turn this into a formal proof. But for the purposes of this class, this more than suffices. So the method of undetermined coefficients is a name of how to come up with a particular solution, because solving the homogeneous solution is something that we know how to do, at least when the coefficients are constants. So this is going to be just like what we did for first order equations. We are going to guess that there's a solution of the same type as the forcing term f of t. Now I know that's a little bit vague, but we'll do some examples so you'll learn what sort of guess will work. So once you do that, you take your guess and you plug it back into the ODE and you solve for any unknown coefficients, like maybe an a or a b or something like that. So let's do an example of this. And this is something that we did for first order, but we'll do it for second order. And again, most books and most classes do not even teach this method until you get to second order. But I think you have an advantage because you see how this works for first order equations. And so then it's not so much out of the blue for second order, but it's more natural. Okay, so let's find the general solution to this equation. Okay, so the first thing to do is to solve the homogeneous equation. That's y double prime minus 5y prime plus 4y equals 0. Now recall that the solutions are going to be e to the rt, and when we plug this back in, we get a polynomial of the form r squared minus 5r plus 4, which is r minus 1 times r minus 4. So your solutions are going to be y1 equals e to the t, and y2 equals e to the 4t. So our homogeneous solution, in other words, actually let me do this in a different color. Our homogeneous solution is c1 e to the t plus c2 e to the 4t. Okay, so now for the method of undetermined coefficients, to get that particular solution, we are going to guess there's a solution of the same type as the forcing term, which is this thing right here. So we're going to guess that there's a solution that is some constant a times e to the 3t. So let's guess that there's a solution yp of t equals a e to the 3t. And then if that's true, then the derivative of that, yp prime, equals 3a e to the 3t, and yp double prime equals 9a e to the 3t. Okay, so let's plug this back in and solve for a. So let's plug back in. So we have 9, come on, pen, 9a e to the 3t minus 5 times 3a e to the 3t plus 4 times a e to the 3t equals e to the 3t. Sometimes it helps to put a 1 right there. So notice this is just y double prime minus 5y prime plus 4y equals e to the 3t. That's exactly what we put right here. So now notice these things are all of the same type, so we can simplify them. We can collect terms. And so what do we have? We have 9a's. So 9 minus 15 is negative 6, plus 4 is negative 2. So we have negative 2a, a e to the 3t equals 1 e 3t. So if that's true, then a must be, so negative 2a must be 1. So a equals negative 1/2. And that means that we have a particular solution. This was our guess. So that means that we have a particular solution, yp of t is negative 1/2 e to the 3t. So that means that we have our general solution, namely y of t is our homogeneous solution plus our particular solution, which is c1 e to the t plus c2 e to the 4t minus 1/2 e to the 3t. And there it is right there. So in this example, we have a different forcing term, one that is sinusoidal. So let's start as we did before by first finding the homogeneous solution. And this is something that we should now be able to do by inspection. This equation is going to lead to a characteristic equation of r squared plus 2r minus 3, which is r minus 1 times r plus 3. And so that means that our homogeneous solution is going to have, let's just write it out, yh of t is c1 e to the t plus c2 e to the negative 3t. Okay, so moving on. There's a problem. So if what I said before is you should always guess a solution that has the same form as the forcing term. So you might want to try something like this. You can say, well, what about finding a particular solution which is a sine of 3t. However, think about what happens if you do this. So if you want to plug this thing back into the left-hand side, right here, and you take a derivative, what happens? Yp prime of t equals 3a cosine of 3t, and yp double prime equals 9a sine of 3t. Oh, and there should be a negative right there, negative 9a. So when you plug this thing back in, this is going to give you sines, this is going to give you sines, this will give you cosines. So there's no way that this cosine here is ever going to cancel out with the sines in the remaining terms. In other words, if you plug this back in and move these two terms, the sines to the right-hand side, you're never going to equate a sine wave with a cosine wave for any value of a. So that is simply not going to work. So here's what we do instead. Well, before I say it's not going to work, it would work if our ODE did not have this middle term in. So if we just had y double prime minus 3y on the left-hand side, then we would not have this cosine problem. So what we do instead is we assume that the solution has a slightly different form. So the, So the fix is that we assume that the particular solution has the form a cosine of 3t, 3t plus b sine of 3t. So if we do this, then the derivative yp prime is 3a, it's negative 3a sine of 3t plus 3b cosine of 3t. And then the second derivative is yp double prime equals negative 9a cosine of 3t minus 9b sine of 3t. So now, if we plug this thing, let's plug this back into here. So plug in, and I'll switch to blue because I can. So y double prime is negative 9a cosine of 3t minus 9b sine of 3t, that's y double prime, plus 2 y prime, that's 2 plus 2 of these, so plus negative 6a sine of 3t plus 6b cosine of 3t. And now, what else do we have? We have minus 3y. So that's minus 3a cosine of 3t plus 3b sine of 3t. Oh, hold on, I should say minus 3y, so that should be minus, so again, this is y double prime. This here is 2y, and this is minus 3y, and we have to set that equal to this. Well, before we do that, let's simplify this. So how many sine terms do we have, and how many cosine terms do we have? Let's see. So how many cosines? We have negative 9a minus 3a, so that's negative 12. So that's negative 12a. Now, how many cosine terms in terms of b do we have? We have 6b cosine. So plus 6b. So this is how many cosine of 3t's we have. Then how many sines of 3t's do we have? So we have, where are our sines? So we have negative 6a, so negative 6a, and then we have, let's see, we have negative 9b and negative 3b, so that's negative 12b times sine and we have to set that equal to the right hand of, we have to set that equal to this, 5 sine of 3t. So we have to set that equal to 5 sine of 3t. Okay, so in summary, we have this has to equal that. So we have this many cosines plus this many sines has to equal 0 cosine of 3t plus 5 sine of 3t. So that better be 0, and that better be 5. Now I did not need to write that 0 cosine of 3t there, but it sometimes helps seeing what we have to do and where we get this system of equations. So let's write down this system. We have negative 12a plus 6b equals 0, and we have negative 6a minus 12b equals 5. So this system, let's see, actually I've done this problem before, so I actually remember what the solution to this is just algebra is. I remember that a equals negative 1/6 and b equals negative 1/3. So what that means is we have a solution of this form for this particular value of the specific value of a and b. In other words, we have a, let's write this down, yp of t equals negative 1, negative 1/6 cosine of 3t minus 1/3 sine of 3t. And so our general solution, y of t, is our homogeneous, let's erase that, is our homogeneous solution plus our particular solution, and that is equal to c1 e to the t plus c2 e to the minus 3t minus 1/6 cosine 3t minus 1/3 sine of 3t. And that is our final solution. Okay, so our next example is to find the general solution to this ODE. So the right-hand side now is a polynomial. So this is the same homogeneous part as the previous problem. So I'm just going to write down that y h of t is c1 e to the t plus c2 e to the negative 3t. And for the method of undetermined coefficients, we have to guess a particular solution, and it has to be of this form. So it has to be a second order, second degree polynomial. So let's guess that the particular solution is at squared plus bt t plus c. And the reason is because, and this is the same form as that, and so if you plug this thing back into the left-hand side and you collect terms, you're going to get a degree 2 polynomial. Some number of t squareds, some number of t's, and some number of 1's. And you can set that, so you're going to have 3 unknowns, and you can set that equal to the coefficients on the right-hand side, 6, 1, and negative 2. And you have 3 unknowns, a, b, and c, and so you can solve that. So let's plug this back in. Well, first we have to take derivatives. So yp prime is 2at plus b, and yp double prime is equal to 2a. So this is going to be a little bit easier than the previous ones because the derivatives are simple. So let's plug this back in. We have y double prime plus 2y prime minus 3y. That's just 2a plus 2 times y prime is 2at plus b minus 3 times at squared plus bt plus c. That's supposed to be a comma after there. It looks like something else. And we have to set this equal to the right-hand side, which is 6t squared plus t plus 2. Okay, so let's simplify. Let's collect terms. Sometimes I like to do it like this. So the left-hand side, well, I guess it's the middle, is going to be some number of t squareds plus some number of t's plus some constant, which is equal to 6t squared plus 1t plus 2. So maybe I should add something like that. Okay, so how many t squareds do we have? We have negative 3a. So we have negative 3a t squareds. How many t's do we have? We have 4a here, and we have negative 3b. So that's 4a minus 3b. And then how many constants do we have? We have 2a, 2b, and negative 3c. 2a plus 2b minus 3c. So this gives us a system of equations. So we have negative 3, well, let's say a word about that. The left-hand side and the right-hand side are both degree 2 polynomials. And if they're the same, then the coefficients better be the same. So this coefficient better be the same, better be equal to 6. This coefficient better be equal to 1, and this better be equal to 2. Okay, so we get a system negative 3a equals 6. We have 4a minus 3b equals 1. And we have 2a plus 2b minus 3c equals 2. So this is a system, and let's see how to solve it. A has to equal a equals negative 2. We can solve that right away. A equals negative 2. So if a equals negative 2, then this is negative 8. Add that onto that side, we get 9, and b is equal to negative 3. And then the last one, well, I can't quite do this in my head, so this last equation is going to be 2a is negative 4 plus 2b is minus 6 plus 3c equals negative 2. This is a negative 10. Add that to here, you get 8, and c equals negative. Oh, hold on. That should be negative 3c. Sorry about that. And so negative 3c equals positive 8, and you get that c equals negative 8/3. So this means that we have our particular solution. We know A, we know B, and we know C. There's one and only one solution. So that means that yp of t equals negative 2t squared minus 3t minus 8/3. So our final solution, y of t, is the homogeneous solution plus our particular solution that we found, and that is c1 e to the t plus c2 e to the 3t minus 2t squared minus 3t minus 8/3. And that is our solution. Let me say one more thing here. Let's suppose, maybe I should have done this as an example, that instead of 6t squared plus t plus 2 on the right-hand side, let's just suppose that the right-hand side did not have these terms. It was just this. In that case, a common mistake is to just guess that the solution has the form at squared and forget about the bt and the c because they're not up here. Well, that would be wrong because when you take the derivatives, even though you don't have a t squared term here, when you take the derivatives, you will get a t and a constant term, and when you plug it back in, you would get down to the same step where you have a system of equations, or you have to equate like coefficients, but now you would have 6t squared plus 0t plus 0. So you would have to set that to 0 and that to 0. And if you did not include b and c, if you just included at squared plus b, or sorry, just at squared, you would have 3 equations and 3 unknowns just like you did before. No, sorry, you would have 3 equations just like you had before, but you would only have one unknown, only a. And unless you're really, really lucky, you're not going to get a solution for that. So the general rule is if you have a degree n polynomial, you should guess that your solution is also a degree n polynomial and include every single term, or include all of the lower degree terms, even if they don't appear on the right-hand side. Okay, so here's another example. This is actually going to be a problem case, and it may not be apparent why. It looks pretty tame, like the first one we did. Well, let's proceed as before, and it'll soon become apparent as to what the issue here is. So the characteristic equation of this is r squared minus 3r plus 2 equals r minus 1 times r minus 2 equals 0. So our homogeneous solution is c1 e to the t plus c2 e to the 2t. So let's proceed as before. It doesn't look that bad. And guess that there's a solution of the form y of t equals, I should probably say yp of t. Yp of t equals a e to the 2t, right? Of the form, the same form as the forcing term. Okay, so let's take some derivatives and plug this back in. Yp prime is 2a e to the 2t, and yp double prime is 4a e to the 2t. So let's plug this back into here and see what we get. So we're going to get y double prime is 4a e to the 2t minus 3 y prime is 2 a e to the 2t plus 2y, 2 times a e to the 2t, it's supposed to be a 2, equals 1 e to the 2t. So let's collect terms, and what do we get? We get 4a minus 6 plus 2 equals 1. So that's a 0 a e to the 2t equals 1 e to the 2t. And there is not going to be anything here. So there's no solution for a. There's no solution for a. So what does that mean? That means there is no solution of this form to this differential equation. There's not a single a that works, because you can't make a anything that's going to make 0 times a equal to 1. You have to set this equal to that. Okay, so first of all, why did that happen? Well, here's why. This forcing term, e to the 2t, notice, actually solves the original homogeneous equation. In other words, e to the 2t solves this equation, y double prime minus 3y prime plus 2y equals 0. Let's put h's here. So if e to the 2t, when you plug it into the left-hand side, always gives you 0, there's no way you can multiply it by a scalar and get something non-zero. So the problem case here is that our forcing term solves the homogeneous equation. So to fix this, there is a simple fix, is to assume that, is to get a better guess. And this is in fact always going to work. Yp of t equals a times t times e to the 2t. So we're, instead of assuming that the solution is a times e to the 2t, we assume it's a times t times e to the 2t. And this, in fact, is always going to work. So let's check. So the derivative of this, yp prime, is, by the product rule, is 2 a t e to the 2t plus a e to the 2t. And the second derivative, yp double prime, so let's take the derivative of this. We get, again by the product rule, 4a t e to the 2t plus 2a e to the 2t plus 2a e to the 2t. So this thing here is the derivative of that by the product rule. So these things can combine and we can get 4a e to the 2t. So let's plug back in. Come on. Plug in. So plug this new guess back into here. And if we do that, y double prime is 4a t e to the 2t plus 4a e to the 2t, this is y double prime, minus 3 y prime, which is 2at e to the 2t plus a e to the 2t plus 2 y times y, which is a t e to the 2t. That's supposed to be a 2 times t. I know it's hard. It's 2 times t rather than, yeah, that's better. And we have to set this equal to e to the 2t. And it's not clear that that's going to work, but this is one of those things like we've seen in a few situations in the past, like variation of parameters. And I think there's one other situation when things massively canceled. And that's in fact why this guess works. So notice how many, so on the left-hand side we have, some number of t e to the 2t plus some number of just plain old e to the 2t. And we have to set that equal to 0 t e to the 2t plus 1 e to the 2t. And fortunately, and now we only have one equation, or one unknown here, a, so that better be 0, and in fact it is. How many t e to the 2t's do we have? We have 4a minus 6a plus 2a. So in fact we do have 0 there. And what do we have? How many e to the 2t's do we have here? We have, let's see, we have 4a and we have 3a right there. So we actually have 1 times a. So now we got to equate coefficients. Fortunately, 0 equals 0. That's in fact why we chose this. This will always cancel in that manner. And a has to equal 1. So we have to equate these two things, and we get a equals 1. So that means that we have found a particular solution of the form yp of t equals, where was it again? That was what it was. 1 times t e to the 2t. So our general solution is our homogeneous plus our particular, which is c1 e to the t plus c2 e to the 2t plus t e to the 2t. So that's, and this again is always going to work. If this thing on the right hand side solves your homogeneous solution, stick a t in front and then proceed as normal. So our next example has a complicated forcing term, but this is actually a combination of two that we've seen recently. So the first thing to do is to, well, solve the homogeneous equation. We've actually seen this before, so I'm just going to write out, that the homogeneous, so the solution to the homogeneous equation is c1 e to the t plus c2 e to the negative 3t. And now recall from previous examples, let's write it like this. Recall that, how do I want to write this? This function, negative 1/6 cosine of 3t minus 1/3 sine of 3. Recall that this function solves this ODE, y double prime plus 2y prime minus 3y equals 5 sine of 3t, and recall that this polynomial, negative 2t squared minus 3t minus 8/3 solves this ODE, y double prime plus 2y minus 2y prime, come on, prime minus 3y equals 6t squared plus t minus 2. And this forcing term is a sum of these two forcing terms. So we are looking for a particular solution that when we plug into the left-hand side equals the right-hand side. So notice, if I plug in this term into the left-hand side, then I get this. That's because of this. And if I plug this term into the left-hand side, that is the left into here, then I get precisely this. So we can, as a particular solution, we can just add these together. So negative 1/6 cosine, should be a cosine of 3t minus 1/3 sine of 3t minus 2t squared minus 3t minus 8/3 is a particular solution. So this solves, let's call this star, this equation star. So the general solution is y of t is the homogeneous plus particular, as always, which is c1 e to the t plus c2 e to the negative 3t plus this creature up here. So that's minus 1/6. Oh, sure, I'll write it up. It'll only take less than a minute. Minus 1/3 sine 3t minus 2t squared minus 3t minus 8. It's funny how this pen sometimes works brilliantly, and other times I can't even make a single mark. Okay, so that is that. Now, this is actually a special case of a more general thing. Let's just suppose, so on the next slide, it'll be the last one of the lecture, I'm going to give you a more general theorem, but let's suppose that instead of 5, this had been 10. And let's suppose that I had multiplied this polynomial by a 3, so it was 9. So in other words, we can do this in our head. Actually, let's just do the first one. Let's suppose that this polynomial, instead of being 5, was 10. So when you plug this thing into the left-hand side, you get 5 sine of 3t. So when you plug twice of this into the left-hand side, you get twice of this, meaning you get 10 sine of 3t. So if instead of these exact numbers, 5 and this ratio, and 6, 1, and negative 2, if we had had scalar multiples of this, if we had had 10 sine of 3t and maybe something else times this polynomial, then our particular solution would just be that linear combination of this guy and that guy. So to summarize what I was just saying, let's suppose this ODE, this linear ODE, has a particular solution yf of t, and let's suppose that this ODE has a solution yg of t. Then this ODE, where the forcing term is not just necessarily a sum of this, but some linear combination, so alpha and beta are constants, has solutions alpha times yf plus beta times yg of t. And so the special case that we did on the last slide was where alpha and beta were both equal to 1, so our particular solution was just the sum of these two things. But this holds in more generality.